Right, so in this next body of work that we're focusing on in mechanics, we're looking at equilibrium. We've already focused on a little bit of this with limiting equilibrium when we're working with friction, but the rest of that work on resolving forces was mostly to do with motion. It was mostly to do with Newton's second law. So a couple of bullet points about equilibrium. So first one, which you would have met at AS, when a resultant of a system of forces is zero, the particle is said to be in equilibrium. So you might get a question where they ask you to resolve and then to reflect on what that resolving tells you. So if it worked out that the x and y resolutions ended up as zero, you could say that the particle is in equilibrium. But an important point to realize is that a particle that isn't accelerating is also in equilibrium. So if it's moving with a constant velocity, that is also said to be in equilibrium. So a particle doesn't have to be stationary to be in equilibrium. The third bullet point we've already looked at in quite some depth when we were working with the previous work on friction. And the other thing to point here is that when a system is in equilibrium, each part of the system is in equilibrium. So at any point you zoom in on the force diagram, you would have equal and opposite forces acting. So in this example here, you would have, if there's a 10 Newton force acting downwards, then there would be an equal and opposite 10 Newton force as a tension acting to counteract that. But if you zoomed in at anywhere else, at any other point on the diagram, you would also have that equal and opposite tension. With the second one, we'd have two different tensions here. You'd have a tension 1 acting in that string, and you would have a tension 2 acting in that string, unless that weight was attached by a smooth ring, as we come to in the next example. And if it is attached by a smooth ring, that means it reaches equilibrium when the tensions are the same on both sides of the ring. So in that case, I wouldn't need a T1 and T2 because they'd be the same tension. Right, so that's the theory. Let's take a look at some questions. So Eg1. So string is tied to 2 points on the same level, so that would be there and there, and a smooth ring of weight 10 newtons. So the smooth ring would be a trigger that you've got equal tensions. Okay, so that would be something that they would be looking for you to recognize on the diagram. And I think actually I've got enough room on the page here to do this. So it's a smooth ring, so I can have a T there and a T there. I'm going to be resolving around that mass, that weight, so I need some angles. Now I can see here that I can create a parallel line with, if I take, as I intend to, positive x to be horizontal and positive y to be vertical, then I've got a 30-degree angle to the horizontal there and a 60-degree angle to the horizontal there. So the smooth ring indicates that those tensions are the same. We've covered that there. And I know it's in equilibrium, okay, because it tells me there. So I can say particle in equilibrium, therefore sum of the x components of the force equals 0, sum of the y components of the force equals 0. Excuse me. So we will resolve now in the same way we were resolving with the pulley questions and the friction on an inclined plane. So the x components, I've got that P acting entirely in the plus x direction. So that's going to be plus T, and it will be cos 60. If you imagine the right angle there, this side is adjacent and hypotenuse, so it will be T cos 60 minus T cos 30, and then that doesn't have any horizontal component, so that equals 0. Then we have our y components, which will be none of that, T sine 60 plus T sine 30 minus 10 equals 0. So I've got two equations with two unknowns, P and T. So you need to look at those and figure your way through them. Hopefully you can see equation 2 has only got T as an unknown. So if we work with that first of all. So from equation 2, if I pull T as a common factor, take the 10 across, then T will be 10 over sine 60 plus sine 30. So on our calculator, I can go straight in, 10 in the numerator, and then in the denominator sine 60 close bracket plus sine 30 close bracket equals 7.3. Now we haven't used G in that because it's been given to us as a weight, so I haven't rounded that. So you could put that as 7.32 newtons, but 7.3 would be fine as well. Now I'm going to need T in my equation 1, so I'm going to store that in X so that I've got that stored, and then in equation 1 P will be T cos 30, that would be positive, minus T cos 60. So on my calculator now, because I've stored that in X, that's going to be X cos 30 close bracket plus, minus X cos 60 close bracket equals 2.7 or 2.68 newtons. So really, given that we are at this point pretty experienced at resolving angle forces at an angle, that should be quite straightforward.